Hello, this is Dr. Heath Van Horn. Today we're going to talk a little bit about IPv6, and it's going to be a brief interview or introduction to the subject. This by no means replaces a full understanding of IPv6, but it is enough for you to get the grasp of the basics. So the reason for IPv6 is that IPv4 has run out of addresses. We knew this problem was going to happen about 15 years ago, give or take, but we found workarounds using network address translation to extend IPv4 because nobody anticipated that IPv4 would explode as it did starting in the mid to late 90s. So as you recall, network address translation, NAT, converts IP addresses on one side of the network to a new address on the other side of the network. That's what your cable provider box, your ISP, does. So if you notice that your home computer usually has a 198 IP address or something similar, you can set it to whatever you want. But when you Google, say, hey, what's my outside IP address, it's usually something much different. That is the NAT adjusting what the internal and external addresses are. This breaks the design of what IPv4 was all about, and we have learned from that. And so therefore, IPv6 was designed to not require NATs. So IPv6 was created in 95. It started earlier than that, but it was formalized in 95. It was deployed in 99. And basically, it has 128 bits available for addressing interfaces versus the 32 bits that were only available in IPv4. So the 128 bits are cut in half. So 64 bits are for the network prefix. That would be like our the equivalent of like a net mask in IPv4. Or if you want to do it metaphor in another way, it would be very similar to like a person's last name, their surname. And they are trying to keep, the community is trying to keep those 64 bits entirely as the network prefix. There are different CITA options, or CITA, depending on how you pronounce it. But they're trying to keep it as CITA 64 as much as possible. Then the other 64 bits is for the interface identifier. They have quit calling them nodes because a node can have more than one IP address. And so therefore they call them interface identifiers. So that would be the equivalent of like your first name. So that way the first 64 bits is the network prefix, kind of a geographical location of what your ISP gives you. And then the next 64 bits is your individual device. Now, IPv6 is different than IPv4 because it also uses hexadecimal notation. And it consists of 8 hextets. So in this example, I show you the 8 hextets, which is 111, 2222, 3333, 4444. So a hextet has a range. Instead of a range of 0 to, that was the cat. Instead of having a range of 0 to 256, a hex range is from 0 to FFFF. And if you want to see the binary equivalent, it is also there. Another thing to take note of, in hexadecimal notation, in straight math, hexadecimals use capital letters. However, when we're using it in hextets for IP addresses, we use lowercase letters. It helps keep the two items separate. So just like IPv4, it's all about the ones and zeros, folks. So in this slide, the hextet range in binary, this is just for one hextet. So instead of 0 through 256, you got 0 through 65,000 per each hextet. So here's an example of a single hextet. And that is where a binary hextet of 0 is broken up into 4 groups, and then a decimal number can be applied. So it'd be the equivalent of 000, but the hex number would be 000 as well, because both counting schemes both use the number 0. As you can see, when you look at when you break up all ones into 4 groups, the first one there is a 1111. Decimally, that is number 15. However, because you cannot represent 15 in a single character, but you can if you do it in hex, the actual character is F. So that's why you have a range of 0000 through FFFF. All right. So when we look at an IPv6 prefix or IPv6 address, it is split exactly in half between the network prefix and the interface identifier. So as you can see here, the network prefix of 1111, 2222, 3333, 4444, we only look at the third hextet and we convert that to a binary representation of 3333. All right. Full representation of the 8 hextet address can be simplified. It is very commonly simplified. And there's a couple of rules that you can use. All leading zeros in any hextet field are suppressed unless the field is all zeros. So in this example, we have the 001 as in the second hextet, and we would not write this as this. We would write it as the image below indicates, that we would suppress the leading zeros and it would just have a 1 located there. In the later on down the number line, and the 7th hextet, that is all zeros, you would not get rid of all those zeros. You would suppress 3 of them and use a single 0 to indicate that hextet does not have any value. So when we do have a longer string of zeros that extends beyond 1 hextet, we do have another shortcut that we can use to suppress zeros. So when we extend the number of zeros beyond 1 hextet, we can use the double colon to indicate that there is a number of zeros in there that we are not indicating at this time. Because we know there has to be 8 hextets, we can get away with this shortcut notation because we know that there's something missing and we just add enough zeros as required to get a full 8 hextets in our numbering scheme. So the representation of an IPv6 address can be simplified. And so we can make many very varied simplified addresses. So a loopback address in IPv6 is noted as : 1. But that's really a bunch of zeros followed by a 1. So you could, using the first rule, is rewrite that entire long string of zeros as 0, 0, 0, 0, 0, blah, 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 1. However, because it is so frequently used, it's just : 1. And that is how that works. So the thing is, you're asking yourself, hey, I've learned IPv4, and it's easier if I think of things in IPv4 instead of IPv6. Okay, so let's go through a simple conversion. So in this case, we have an IPv4 address of 192.0.2.128. Just like in IPv4, in order to understand what those numbers mean, you need to convert that to binary, because those numbers literally don't mean anything. They are numbers that represent the number of ones and zeros in an octet. Now we're looking at the number of ones and zeros in a hextet, so that's slightly different. So when we look at the binary, we convert the binary, or the IPv4 decimal, to a binary representation, and then we break up that binary representation into hextets. And you can see here that 192 octet is turned into a 11000000 binary representation. But when we convert it to a hextet, we got to break those two blocks in half, and that gives us a 1100, which gives us a Charlie, which is 15. Okay, and so when we that's not 15, that's 12. So the thing is, that is where we get that information from, because the first position 1, and in the octet, the first position 1 is 128. However, when we do it in hextet, the first position 1 is an 8, and the next one is a 4. So that's where we get the 12 from, and the 12 becomes C. So, and then everything else, we do the same conversion. As we go through, because we've broken everything, all the octets up into hextets, we got the 0, 0, 0, 0, and then the hextet of 0010 is a 2, and then we have a next hextet of 8, and then the final hextet of 0. So we rewrite that conversion into 2 hextets of Charlie 000 and 0280. Now, if you look at the binary and the hextet prep, you can see that all the ones and zeros are all exactly the same. Nothing has been changed. The only thing that has been changed is how those ones and zeros are read. Okay, so not red as in the color, but read as an R-E-A-D. So instead of reading the ones and zeros as an octet, we're reading them as a hextet. So, because nothing has changed in the number of ones and zeros in a string of 64 characters, that is why 192.0.2.128 can be rewritten as Charlie 000:0280. So that can be very confusing to people. However, when you stop looking at the IPv4 address as numbers, and you stop looking at the IPv6 address as numbers, and you remember that they are simply representations of ones and zeros, it gets a lot easier to understand how this works. So if we have a network prefix for IPv4, it is all zeros with an FFFF. So to convert an IPv4, we just simply insert FFFF before our IPv4 address that has been converted, and that tells everybody that this IP address used to be an IPv4 address because of those 4 Fs that are in there. Sorry about that. The dog had to go out. Okay. So now that we have that new address for our old IPv4 network address, we can rewrite using our zero suppression rules by eliminating the leading zeros. And so we got all the hextet preceding zeros reduced down to 2 colons followed by FFFF and the representation of our IPv4 address. And then we can go one further and suppress the leading zero in the last hextet and just write 280. All right. Again, when we convert IPv4 to IPv6, we have not changed any of the ones and zeros that represent that device. All we have changed is the human understanding of what those, of the labels of what those ones and zeros are. So we've changed the human representation of that 64-bit string of ones and zeros that represented 192.0.2.128, and we converted it to the IPv6, which is actually Charlie 000:280. Those, the last 2 hextets in an IPv6 address and the 4 octets of the IPv4 address use the exact same number of ones and zeros. They are the exact same thing. All we're trying to do is to take a large string of ones and zeros and simplify it in a way that you can make sense of it, the human. All right. So here's an example of more abbreviation. I missed some of the capitalization here, so forgive me. But so if we look at the example above, Foxtrot Echo Charlie 2 with 0000, 78 Charlie Alpha 00, 23 Alpha Bravo can be abbreviated by taking out the first 3 zeros and then replacing those with a colon, or a double colon, I should say. Or you can leave the first 3 zeros and reduce the second 2 zeros next to each other and place it in a double colon. Either which is fine. Doing it to the leftmost set of zeros is kind of the rule. However, when you're typing in a address, either will be acceptable. So that works pretty good. But the standard, and whether or not it'll allow for sloppy programming, I don't know. But the standard is only the leftmost zeros can be replaced by the colon. So never, ever, ever replace both segments of zeros in this example with the double colon, because you have 5 zeros there. If you replace them both, you have no idea whether the first double colons are 4 zeros or 2 zeros or 3 zeros. You just don't know. So therefore, do not ever replace more than one set of successive zeros with the double colon. All right. So let's talk about the IPv6 prefix a little bit. The first 64 bits of the IPv6 address can be divided into parts. Some people do this, some people don't. So the thing is, it's typically used where your geographic region, so we'd be the Northeast region or this side of the Mississippi region, it just depends on what the ISPs decide. That's what they would use for the 64 bits of the IPv6 address. It may not use all 64 bits. That might reserve some of those bits for, they might only use 32 of the bits for the geographic location, and then the ISP can append those bits, and then the network that you're actually using can add more bits. However, the whole point is that prefix is unique to a certain network. So there is no NAT tables used in IPv6 because the prefixes are all unique. So when you use the prefix all by itself, you use CITA notation. So when you're using it just by itself, you can see this example here that it's using CITA 64. That way you know how many zeros. You see the double colon there. You know how many zeros you have to insert just in case you have to put them in there. So that is how that works. It is referred to as the global routing prefix. This is a term that has been tossed around for a while. I don't know if this has really caught on yet, but even though this technology has been around since '95, it's been deployed since '99, it really has not caught on because that is a lot of digits for people to remember, and they'd rather use just IPv4. However, since we ran out of IPv4, we have to make this adjustment where we force the learning of IPv6. Okay. So in IPv4, we used to call every device a host. We don't do that anymore. We call it an interface ID because a host is a device that communicates with the internet. However, devices can have more than one interface to the internet or to the network for various reasons. So therefore, they say do not refer to IPv6 as a host address because you want to refer to it as an interface ID, especially with the Internet of Things. You want to make sure that you're talking about a specific interface on that device. Okay. It must be unique within the network, and to create that unique ID, we use the layer 2 MAC address. So we will get into that next, where we talk about how the MAC address is used to create an automatic unique identifier for the IPv6 interface ID. So in this case, we have a PC. Its MAC address is published right here. And we have 5 basic rules to convert the MAC address into an IPv6 interface address or interface ID. So the first rule is we split the MAC address into 2 halves. We insert FFFE between the halves. Now remember, FFFF indicates that whatever follows is an IPv4 address, and FFFE indicates that this identifier is based off the MAC address of the component, electrical component itself. Once we do that, we convert the first 2 hex digits to binary. The 7th bit from the left is also called the universal local bit, and we change that to 1 if it isn't already. And then we convert everything back to hex, and then we put it all back together. Okay, so I know that's fast. I have a couple slides here to help break it down. All right, so this is the same MAC address of the previous example. So the first thing we did was we split the MAC address in half. So we moved the first 3 to the left and the other 3 to the right, and then we inserted the FFFE. You can see that by the bold type. We inserted in that gap the FFFE. Then we converted the first 2 hex digits to binary, which 2 is 0010, and then 0 is obviously 0000. So now on bit 7, we start counting 1, 2, 3, 4, 5, 6, 7. We flip that bit to a 1, and now we convert it back to the hex. So now that number 20 has turned into 22, and don't get hung up on how that how flipping that bit just adds 2, because you have no idea what those first 2 bits are going to be, and so it'll not always automatically set that to 2. But so you can see that, and then when we put everything back together, we can see the MAC address has only changed slightly, and is now an interface ID. It's 22 0 Charlie, Foxtrot Bravo, Foxtrot Foxtrot, Foxtrot Echo, Bravo Charlie, Alpha 007. And that would be the 64 bits after the identifier. So that is how you use the MAC address to create an IPv6 interface ID. So IPv6 doesn't use a broadcast address. It uses different address types. So a link local, that's all you use with a current subnet. It always begins with FE80, and it's only 10 bytes in length, or bits in length. So it is used to set up an establishment with your DHCP server, neighbor discovery, hey, who's next to me on the network, and then, or sometimes if you don't have any routers on your network, you're just doing PC to PC or switch to switch, it will be used to communicate those devices of who is connected to the network. A unique local is used between networks, not using public infrastructure. So this is an address that you can create for yourself, and it is only used on your network. It cannot leave your network because the ISP will reject a unique local address. And then there's global unicast, and this is the one that we really want, is that your ISP will assign you based on geography generally, between 32 bits and 56 bits long, and then the remaining bits are spaces for you. So you can create your networks by just appending the ISP address, and you can just build your network from there. So that makes things much simpler than trying to use a NAT table and trying to figure out how this packet keeps changing numbers, because this will be a global number unique to that interface. So this is quite a useful tool, and it makes deployment of network devices a lot easier. You probably have a ton of questions. I did this video in one take. I don't have time to do a second take because I've had to take down much complicated material and try to condense it into something that is relatable that you guys can do on your own, since we are not in the classroom. So please forgive me. There is lots of guides and other material out on the web. I suggest you use them as much as possible. And with that, you can contact me through the normal channels, and I will answer all questions that you have. And with that, I conclude this presentation. Thank you very much.